I hate chemistry. It's too much work for me. I hate chemistry. It's too much work for me.
Okay, class, settle down. My name is Miss Ria, and you are in Chemistry 101. Today's topic is gas laws.
Oh, why gases?
Well, that's an interesting question.
So what makes these loosely clustered particles unique? They are easily compressed and mixed completely with any other gas. Gases also exert pressure on their surroundings unequally. This pressure is measured by dividing force over area. There are several units of measure for gases, the standard being atmospheres, which can be converted into other units such as millimeters of mercury, torr, and kilopascals.
An ideal gas is a gas which follows the kinetic molecular theory. There is no such thing as an ideal gas. However, there are real gases that behave ideally. Real gases exhibit behavior that is closest to the ideal behavior of low pressures and high temperatures. Characteristics of ideal gases include that the molecules do not attract or repel each other and that they take up no volume.
So, as we just learned, all gases behave less than ideal.
This class is less than ideal.
There are four major parts to the kinetic molecular theory. Number 1, particles are so small compared to the distance between them in gases that the volume of the individual particles is negligible and considered close to zero. Number 2, particles are in constant motion. The collisions of these particles with the walls of their containers causes the pressure exerted by the gas. Number 3, particles are assumed to exert no force on each other. They neither attract nor repel each other. Number 4, the average kinetic energy of a collection of gas particles, which is the average energy of motion of a collection of gas particles, is assumed to be directly proportional to the temperature of those gases in Kelvin.
So, class, there are four main gas laws.
There are 4 of them?
Don't worry, they get combined into one later.
Number 1 is Boyle's law. No, not him. That's more like it. This law relates pressure and volume, showing their inversely proportional relationship at a constant temperature. When this equation is manipulated into a y equals mx plus b form, the slope of the graph is equal to the constant of proportionality. The x-axis is 1 over pressure, the y-axis is volume, and the y-intercept is 0. To calculate the constant of proportionality, a proportion must be set up. Since the two are inversely proportional, the proportion is set up as such. Changes in the value of PV are only significant at high temperatures. KMT justifies this law, because as you decrease the volume of the container, the gas particles have less room to spread out, and therefore collide with the walls of the container more often. According to KMT, more collisions increase the pressure, which does support this law. Number 2 is Charles' law. No, again, it's not him. There we go. Charles' law is a special case of the ideal gas law. It states that the volume of a fixed mass of a gas is directly proportional to its temperature. This law applies to ideal gases held at a constant pressure, where only the volume and temperature are allowed to change. The formula for this gas law is V1 over T1 equals V2 over T2. Number 3 is Gay-Lussac's law. This law states that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. As the pressure goes up, the temperature also goes up, and vice versa. The formula for this is P1 over T1 equals P2 over T2.
Number 4, Avogadro's law. This law relates volume to the number of moles of gas particles, showing the directly proportional relationship at constant temperature and pressure. To calculate the constant of proportionality, A, the equation written on the board is used. This law is usually obeyed at low pressures and is strictly dependent on the number of gas particles, not on the volume of the individual particles.
Remember when I said that all get combined into one? Well, here it is.
Wait.
The previous laws all assume that the gas being measured is an ideal gas, a gas that obeys them all exactly. Since according to Avogadro, the same volumes of gases contain the same number of moles, chemists could now determine the formulas of gaseous elements and their formula masses. The ideal gas law is as written on the board, where N is the number of moles and R is a constant called the universal gas constant, and is equal to approximately 0.0821 liters ATM per mole Kelvin.
So guys, there's two other laws that don't fit into the ideal gas laws. There's Dalton's law of partial pressures and Graham's law of effusion and diffusion.
There's 2 more of them? You're telling me there's Charles, Boyle, Gay-Lussac, Dalton, Graham, and avocado?
It's not avocado, it's Avogadro.
I'm hungry. When's lunch?
Effusion is a process in which a gas escapes from a container through a relatively small hole, while diffusion is the net movement of molecules or atoms from a region of higher concentration to a region of lower concentration, or put simply, the spreading out of molecules. Graham's law of effusion and diffusion states that as the molar mass of gas particles decreases, the rate of effusion and diffusion increases. The formula is the following, with mm being molar mass. Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. KMT supports this law as well. KMT assumes that all gas particles are independent and the volumes of each particle are negligible. The identities of the gas particles do not matter, and each gas's pressure can therefore be added together to obtain the total pressure.
So class, what did we learn today?
Gas laws and avocados.
Okay, class.
No, can we
Now that we've discussed a little bit about gases, let's discuss the difference between real and ideal gas. Oh, that sounds bad. Do it again, do it again. Go.
Oh, why gas it? There's 2 more of them? You're telling me there's the Charles, Boyle, Gay-Lussac, Dalton, Graham, and now wait, sorry.